right, let's have a look at two questions from our homework on page 301 from last night, starting with question number 1. Number 1 on page 301 says, a force of 125 newtons causes the springs to stretch a length of 0.250 meters beyond its equilibrium position. So they're not telling us anything different there. The term they use here is a little bit different. Beyond its equilibrium position, that just means that's how far it's stretched, right? Its equilibrium position is its normal position, so it's stretched 0.250 meters. What's the elastic potential energy stored? And if the spring contracts to stretch 0.15 meters, what's the change in elastic potential energy there? Let's deal with A first. In question A, we have a force here of 125 newtons, and we have a displacement, or an amount of stretching of 0.250 meters. We want to find the elastic potential energy. Zach, we get two equations that we're allowed to use here. What are those two equations that we're allowed to use? Doesn't matter what order you give them to me in. Good. EP is equal to 1/2 kx squared, and the other one is? Good. F is equal to kx. So which one do you want to try first? You don't have to know which one to try. Okay, just tell me one to try first. Okay, well, sounds good to me. EP is equal to 1/2 kx squared. That sounds pretty logical, actually, since that's what we're looking for here, trying to solve for the potential energy. That's probably the one that I would try first as well. But we do have a problem with that, and that is we don't know what k is. So how do you suggest we find k? Good. Let's find k by using F over x. F is 125 newtons, and x is 0.250 meters. And Jillian, what did you get for that? 500 newtons per meter. All right, now we can plug that back into here. 500 newtons per meter, 0.250 squared. And what do we get for a final answer there? 15 point. Any more decimal places? Nope. 15.6 joules. And we're going to round that to the three significant figures, I guess, that we already have it rounded to. So there's our answer to A. 15.6 joules is the elastic potential energy. Now, question B, we're reducing it to 0.150 from 0.250 meters. What do you think is going to happen to the potential energy? Is the potential energy going to increase or decrease here? It's going to what? It's going to decrease because the amount of stretching is less, right? Well, we can find the potential energy there as well by saying EP is equal to 1/2 kx squared. Same thing as we did right there. The only thing that changes here is the displacement, right? Because it's the same spring, the spring constant's got to stay the same. So if we were right when we said it was 500 before, then it's going to be 500 again. Now, the displacement here is, instead of 0.250, it's 0.150. We're going to square that. And what does that work out to be now? What is it? 5.625? 5.625? All right, so there's the final potential energy. Now we're looking for the change in elastic potential energy. So Zach, if we're looking for the change, what are we going to do here? Right, we're going to just simply subtract the two. So 5.625 minus 15.6 gives me about 10, right? Almost 10. Actually, it would be not 10, negative 10-ish, right? And what does the negative mean? It's a decrease, right? Not that it's left or right or up or down or north or south or east or west, but it means that it's a decrease, right? Delta E is a scalar, so it doesn't mean it can't be a negative. It just means it doesn't have a direction associated with it. All right? The other one on that set on page 301 that we wanted to go over was question number 5. Number 5 says, this is a good question actually. When a spring is stretched by 0.4 meters from its equilibrium position, its elastic potential energy is 500 joules. What's the magnitude of the force required to produce this amount of stretch? Zach told me in the last question that there's two equations that I'm allowed to use here. F is equal to kx and EP is equal to 1/2 kx squared. That doesn't change here either. Same two equations we're allowed to use for this problem as for that other problem. We're going to use them a little bit differently though. We have this time a displacement of 0.400 meters, and we have an elastic potential energy this time of 500 joules. We want to find the force. We'll worry about question B later on. Probably looking for the force, probably going to use Kx, but we got a problem with that. We don't know what K is. All right, how are we going to find K? Using the other equation, right? EP is equal to 1 half Kx squared. So we're going kind of backwards this time compared to the last question. EP is equal to 1 half Kx squared. Let's solve for K. Let's take the half over by multiplying by 2. Divide by x squared equals K. So it becomes 2 times 500 divided by 0.4 squared. And what does that give me here? 1,000 divided by 0.4 squared is 6,250. And now we're going to multiply that by 0.40 meters to get the force. Get 2,500. We're going to round that actually to 3 digits, so we're going to say 2.50 times 10 to the 3 newtons. Are we good with that? I almost said almost exactly the same thing as the last question, but really it's the opposite of the last question, right? Same equation, same topic. In the end, we have 2 equations. We needed the value of K for both of them. We didn't have the value of K, so use one of them to get K and then plug it into the other one. Okay, that's a pretty common thing to see. Now, question B says, if the force causing the stretch is now changed to 1,000 newtons, how much change in the elastic potential energy results? If the force changes to 1,000 newtons, how much change in the elastic potential energy results? Well, there is a change in potential energy, but what else changes? If force changes, what else changes? Actually, let me ask you another question first. If force changes, what does not change? What stays the same, Julia? The constant. Good. K stays the same. All right. Now that we know that K stays the same, when force changes, what else changes? The displacement, the value of x. So let's use F is equal to Kx to find the new value of x. The force is now 1,000 newtons. K is the same, and it was 6,250. So we're going to say it's 1,000 divided by 6,250. Gives me 0.16 meters. And now I can find the potential energy, the final potential energy, by saying 1/2 times Kx squared. 1/2 times 6,250 times 0.16 squared. Still not going to be my final answer, though, although it's close. 0.5 times 6,250 times 0.16 squared gives me 80. What was my initial energy? 500. What's my final? 80. What's my change? Negative 420 joules, right? 80 minus 500 joules. See what we did there? Okay, the key to that was exactly what Julia told us a minute ago, and that is that K doesn't change. Unless you change springs, K stays the same. And you know what, guys? Listen, if you recognize that K isn't changing, you got to just try things, right? There's only 2 equations. If K stays the same, there's only 2 equations. It's got to work out for you if you keep trying. It has to. Okay, let's say that you assuming you recognize K stays the same, and you started with EP first instead of F is equal to Kx. Well, you would have discovered that you wouldn't have been able to find it. So you would have went to the other equation, and then you would have found something, and then you would have went back to the first equation, then it would have worked out for you. Okay, so eventually, questions like this, as long as you recognize K doesn't change, it's got to work out for you, as long as you keep trying those 2 equations. All right? All right, the new section of our unit is called mechanical waves. A mechanical wave, by the way, is a wave that requires a medium versus an electromagnetic wave which we'll look at in Physics 30, that doesn't require a medium. For instance, a mechanical wave can travel through air or water or something like that. An electromagnetic wave like visible light or X-rays or gamma rays can travel through empty space. We're going to focus on the waves that require a medium. In general, waves are a means of carrying energy from one place to another. Whether we're talking about electromagnetic waves or mechanical waves, but specifically for mechanical waves, they're a means of carrying energy from one place to another through a medium, through water, through air, through metal, through the wall, versus electromagnetic waves that also carry energy from, say, the sun to the earth, but can do it through empty space. And as you saw in the demonstration that we just did, a wave is really just a simple harmonic motion of the individual particles carrying the energy. So person A is down here, person B is right here. The wave transmits the energy from person A to person B, but each individual particle along the way is undergoing simple harmonic motion. The simple harmonic motion of this guy, the energy in the simple harmonic motion of this guy, gets transferred to the simple harmonic motion of this guy, gets transferred to the simple harmonic motion of this guy, and so on. So it's all simple harmonic motion, but as we go, the energy gets transferred from one particle to another. The particles, and this is a little bit of a misconception, the particles from person A don't actually travel to person B. I've had a cold the last few days. You don't need to worry about the particles from my throat and the viruses that go along with the particles in my throat entering your ear and giving you an ear infection. Even though you can hear my voice, it doesn't mean that the particles are carrying the sound directly from my throat to your ear. Now, the wave carries the sound. The wave requires the particles, but the particles don't go from me to you. The particles just vibrate in simple harmonic motion in their own little zone, in their own little place. There's a particle that's right in front of my mouth that vibrates, which causes another particle right in front of it to vibrate, which causes another particle right in front of it to vibrate, and eventually causes a particle right in front of your eardrum to vibrate, which eventually causes your eardrum itself to vibrate. Means of carrying energy from one place to the other, they're really just simple harmonic motion of individual particles, not the movement. I was going to say not the movement of particles. It really is movement of particles, right? Simple harmonic motion, but in their own little place. Now, there's two kinds of waves, two kinds of mechanical waves that we're going to look at. One's called a transverse wave, and one's called a longitudinal wave. Our two kinds of waves are transverse and longitudinal waves. You saw the demonstration just a minute ago. You know that a transverse wave looks like this. It's like what we think of as a wave, right? When we picture a wave, this is what we picture as a wave. A transverse wave. In a transverse wave, the wave motion might be to the right, but the particles are all vibrating up and down. The individual particles are vibrating perpendicular to the way the wave is traveling. In a longitudinal wave, and it's a lot harder for me to draw this, but bear with me here. In a longitudinal wave, we have this series of areas where it's squished or it's higher density, and then we have these areas that follow it with lower density or where it's stretched out a bit. If the wave, the longitudinal wave, is traveling to the right, then the individual particles within the longitudinal wave are traveling right and left in their own little zone. In other words, they're traveling parallel to the way the wave is moving. Let's take a closer look at what kind of wave is this again? This is a transverse wave. Let's take a closer look at the transverse wave and label a few parts of it. We have a graph here on this transverse wave. It's y versus x. So it's y position versus x position. And you can see the the wave motion right here. And you can see the particle motion is perpendicular to the direction that the wave is moving. Let's label a crest first. A crest is the top of a wave. It's like a crest of a hill. When I was growing up in Nova Scotia, they have they have these signs. You know, I don't think you see them in Alberta, but I don't think I've ever seen one in Alberta actually. But in Nova Scotia, sometimes you'd go over a hill, over the top of a hill, and there would be a sign coming up to the top of the hill that would say "Blind Crest." And what that meant was that you're driving up a hill, and then you're going to go over the top of a hill, but you couldn't see over the top of the hill. Maybe there was a road coming out perpendicular to that on the other side of the hill. So maybe someone would be entering the highway perpendicular to the road on the other side of the hill. And basically they're saying, look, watch out, because you can't see over the hill. You can't see over the crest of the hill. So maybe there's going to be a car coming out right in front of you. You just got to be careful. Watch out. Blind crest, blind top of the hill. Okay, the crest of a wave is the top of a wave versus the trough. The trough of a wave, which is like kind of like a feeding trough, right? If you look at a feeding trough as a cross section, you know, in a barn or something, then it would be like a half pipe, right? All the food is in that half pipe, that trough. Okay, the bottom of a wave is a trough. We'll define the crest as the top of a wave. And we'll define the trough as the bottom. Wavelength. Well, there's a tough one to define. Let me tell you. Anybody want to take a stab at it? The length of a wave. How long a wave is. Don't ever forget that one. You're not really supposed to define something in terms of itself, but I think it's okay this time. It's the length of a wave. Now we're going to assign a symbol to this. This is going to be kind of foreign to you. We're going to use a Greek letter called lambda. It's like an upside down Y. Lambda. And the length of a wave is going to coincide to the distance over which the wave repeats itself. And that could be from crest to crest. Okay, that's a wavelength. A wavelength could also be from this position. Okay, I'm going to start right here. I want you to tell me when a wavelength measuring from this position stops here, okay? Just yell stop when I reach one complete wavelength. Is that it? That's not a wavelength, right? Tell me when to stop. You guys are going to do it, I know. That's a wavelength, right? Okay, from this position to this position is the distance over which the wave repeats itself. That's one complete wave. Okay, the length of a wave. We could go from here. If we go from here, where are we going to? Tell me when to stop. Yeah, the distance over which the wave repeats itself. Lambda, Greek letter, upside down Y. Now the amplitude of a wave is the height of a wave. But you got to be careful with that. It's measured from the equilibrium. And what we mean by that is it's measured from that x-axis there. In other words, this would be the amplitude. The height of the wave measured from the equilibrium. Or you could do it down here. That would be fine as well. But it's got to be measured from the equilibrium to the top of a wave or to the bottom, top of a crest or to the bottom of a trough. The amplitude of a wave is related to the energy. Not directly related to energy, but it's related to energy. In other words, uh, the higher the wave, the bigger the wave, the more energy it carries, right? And that you guys have to have some kind of intuitive notion of that, right? If you're swimming off the coast of California and these little waves are coming in, and now all of a sudden this big wave comes in, everybody starts laughing and screaming and running away from it, right? Why? Well, because intuitively you know it carries a lot more energy. When it's a bigger wave, it carries a lot more energy. In fact, if the wave is double the size, it carries about 4 times the amount of energy. If it's 4 times the size, it carries about 16 times the amount of energy. So it's not a linear relationship. As the amplitude doubles, the energy doesn't double. Okay, as the amplitude doubles, the energy quadruples. But it is related. All right? Now the other kind of wave, and if the last diagram I do for a longitudinal wave was poor, then this is even more poor, I think. But the last kind of wave showed particles vibrating perpendicular to the way the wave is moving. This one shows it vibrating parallel. Each of the individual particles are vibrating back and forth in their own little zone, parallel to the direction of the wave motion. Now, instead of having crests and troughs, we have what's called compressions and rarefactions. Compression and rarefaction. A compression is a zone like this where you have higher density. In other words, the material that's carrying this wave is scrunched together. You guys saw in the demonstration I did a little while ago, when the slinky wave was going down there as a longitudinal wave, you guys saw this area where the slinky was compressed. That was the compression. The rarefaction, on the other hand, is the area that follows and leads that compression. That's an area of lower density. That's where the slinky or whatever medium we're using is going to be spread out a little bit more. It stands to reason that if we have an area where the slinky is compressed, where it's all squished together, we have to have an area behind it where the slinky is stretched. Sound waves travel as longitudinal waves. Earthquake waves typically travel as longitudinal waves. Now, that doesn't mean the energy can't go into a transverse wave, right? Like I talked about the earthquake in the middle of the Indian Ocean 10 years ago. That was longitudinal waves. Now, when that longitudinal wave hit the bottom of the ocean, okay, then it caused in the water a transverse wave. So the energy was transferred from the Earth through the Earth as a longitudinal wave, but then into the water as a transverse wave, carrying energy to the land and eventually to halfway across the world. So how do waves move? Well, they carry energy from one place to the other, and they do it sometimes in a remarkably efficient way. I told you guys the story of how the earthquake in the Indian Ocean, it caused the tsunami that wiped out 150,000 people, transmitted energy to the other side of the world off the coast of Nova Scotia 30 hours later. Okay, sometimes it does it in a remarkably efficient way. Sometimes it does it pretty quick too. The speed of the wave is how fast the wave is moving, how fast the energy is being carried. And the wave travels at a constant speed. So we can represent the motion of that wave quite simply by using the equation V equals D over T. The very first one we learned that represented the constant speed of a car or constant speed of a person walking. But just like the equation v equals d over t that represented constant speed for circular motion, we're going to tailor this equation specific to waves. Remember with circular motion, the distance of the circle once, the distance around the circle once was 2 pi r, and the time around the circle once was period, so d over t became 2 pi r over t. Remember that? What's the distance over which the wave repeats itself? The distance over which the wave repeats itself is called the wavelength. So we're going to replace delta d with lambda. What's the time over which the wave repeats itself? What's the time over which the wave repeats itself? The time, let me rephrase that. What's the time for one complete cycle of a wave? The period. So V is equal to d over t, but it's also equal to lambda over t. Now, usually what we do, we could use that as our equation, but usually we actually replace t with 1 over f. So it becomes lambda over 1 over f, which becomes f times lambda. This is the equation that we want to get to right there. V is equal to f times lambda. That's on our data sheet, as is this, although in 2 different places. You're going to use both of these to describe the motion of a wave, the speed of a wave. This equation, by the way, this one that's really just a special form of V equals d over t, but specialized to waves, we often call the universal wave equation. The universal wave equation. And one more little thing before I do an example, I'll give you a couple questions to work on. It's important to note that this variable right there, the frequency, once a wave has been made, once a wave has been produced, the frequency never changes. The speed can change. When water goes from a deep depth to a shallow depth, it slows down. That's why the wave breaks. When the water comes into the shore, the wave breaks, right? Because the speed changes as the depth of water changes. When sound goes from air into water, it speeds up. The speed of the sound changes, the speed of the wave changes. The speed can change, and so can the wavelength. But the frequency of the wave, once the wave has been made, the frequency stays the same. In other words, how many waves you have per second is simply dependent upon what caused it. If I put my hand down in the water at 10 cycles per second, that's the frequency of the wave. That wave's been made. Can't change it. Unlike the speed and the wavelength, which can change. Quick example, then we'll do a couple practice problems, and then we'll be finished. To generate waves, this is chapter 8 now. Look at this. Now we're fast forward into chapter 8, which is the last chapter we do in Physics 20. To generate waves in a stretched spring, you oscillate your hand back and forth at a frequency of 2 hertz. What does that mean? 2 cycles per second. So I'm going to oscillate my hand back and forth like this, like I was in the demonstration a little while ago, 2 times per second. The speed of the wave in the spring is 5.40 meters per second. What's the wavelength? Well, we're going to say V is equal to f times lambda. We're also, by the way, allowed to say V equals d over t, but I don't think that's going to be very helpful to me in this question. To rearrange this to solve for lambda, I get V over f. V is 5.40 meters per second, and f is 2.00 hertz. Gives me 2.70 meters. Real quick question before I give you those practice problems to work on here. Three variables in this equation. If this wave went from, let's say, one slinky, metal slinky to a plastic slinky, let's say they were attached, plastic slinky attached to a metal slinky, two variables of the three would change. One of them would not. Tell me which variables would change and which one would not change. As the wave goes from metal slinky to plastic slinky, the wavelength would change, the speed would change. I don't know, to be honest, whether it would speed up or slow down. Probably speed up a little bit would be my guess, but I don't know for sure. But we know the speed would change a bit, the wavelength would change a bit, the frequency would stay the same. Because once a wave has been made, the frequency always stays the same. Questions that we want to work on for the next few minutes in class here, page 409, questions 1 to 3.